Good afternoon. This is Engineering Mechanics Statics. And we've been working in moments, both scalar method and vector methods. So let's chug through some problems. Start with problem 8. This is page 96 in the Hibbeler text, 5th edition. Pearson publisher. Okay, 3.8 states, determine the moment of each of the three forces about point B. You have an F1 here. This angle is 30 degrees. You have an F2, 300 newtons. Let's put that over here. This angle here is 60-degree angle. This is F2, 300 newtons. F1 is 250 newtons. Distance here is 2 meters. Distance here is 3 meters. That's up to here. You have point B. You have an F3. And this is 500 newtons. This is a slope triangle, 3, 4, 5. And this distance here is 4 meters. So the moment of each of these three forces about point B, remember we need to find the perpendicular distance between the line of action of the force and the point of interest that the force is causing a rotation about. And we state our basis that counterclockwise rotation is positive, clockwise rotation is negative. So for F1, we have 250 newtons. Cosine of the 30-degree angle gives us the vertical component. And then the perpendicular distance between the line of action of the vertical component and point B is given to us as 3 meters. And since that is pushing down to the left of B, it's counterclockwise rotation about point B, which means it's positive. Now the horizontal component will be sine of that angle. And that is pushing to the right, so it's causing a clockwise rotation about point B. So it's negative direction, so it's 250 times sine of 30 degrees. And the perpendicular distance, the line of action of the horizontal component and point B is given to us as 4 meters. Multiply this out for F1. So in the moments about point B gives you approximately 150 Newton meters. Now for force F2, some of the moments about point B. F2 is a 60-degree angle. The horizontal component is given to us as cosine of 60. horizontal component. And the perpendicular distance between the horizontal component of F2 and B is given to us as 4 meters. The horizontal component is directed to the left, so it will be causing a clockwise rotation about point B. So that gives us, counterclockwise about point B, so that gives us positive. Remember, moments, force times perpendicular distance. Now, the vertical component of the F2 force, this line of action goes through point B, so there is no perpendicular distance. So F2, the vertical component, does not cause a moment about point B. So for force F2, multiplying this out, you get approximately 600 Newton meters. Once again, F3, both the vertical and horizontal components go through point B, so F3 causes no moment about point B. Let's move along. Let's look at problem 321 on page 98 of the text. Here it states, in order to pull the nail out at B, a force F exerted on the handle of the hammer must produce a clockwise moment of 500 pounds force inch about point A. Determine the required magnitude of force F. So we're saying we need to produce a clockwise moment of 500 pounds force inch. So we know clockwise, we need a moment of, we'll say, with counterclockwise being positive, negative 500 pound force inches, because clockwise means negative. So force F has an angle here. I'll try to draw it out. The angle being 30 degrees. The distance from the tail of point F where it acts at the hammer and point A, this is 18 inches. And then there's an offset between, say, point A here and this line of action. This is 5 inches. Therefore, we said the moment about point A is 500. So then what we have to find the force F. So F, the horizontal leg will be cosine of 30, and it's pulling to the right about point A, so it's causing a clockwise rotation, negative. So it'll be negative F times, we said the horizontal leg, cosine of 30 degrees. Now, what's the perpendicular distance between this horizontal component and point A? Well, that's the 18 inches. And then the vertical component will be sine of 30, and the point A, the perpendicular distance between this and the line of action of the vertical component of F is 5 inches. And once again, that's pulling up around to the clockwise about point A. So that would be minus F sine of 30 times the 5 inches. Solving for this, you get F, 27.6 pound force. All right, let's move along a little bit tougher. Let's go on to problem 329. This is page 99 of the text. Here, it says the force F, they give you it in Cartesian notation, 400I, 100 minus 100J minus 700K, pound force. Acts at the end of the beam. So I'll try to draw the beam. This is three-dimensional space. This is our point O. Okay, that's pretty much the best I can do, drawing wise. Let's get this down here. Okay. Copy that. Here's another problem. Okay, so we have a force F acting at point B. This is our y-axis, z-axis, x-axis. They give you this offset distance here, 0.25 feet. You give you this vertical distance in the z direction here as 1.5 feet. And the length here of the beam is given to us as 8 feet. And the question asks us to determine the moment of this force F, given to us 400I minus 100J minus 700K about the point O here. So we know vector notation, the moment about point O is R cross F. Now R in this case will be our position vector from the origin O to point B. Well, remember, this is just the difference in the coordinates of the 2 points. The coordinates of point B in the x direction from the origin is 0.25. I'm sorry, in the x direction, it's 8. In the y direction, is 0.25. And in the z direction, is 1.5. So let's write that. In the x direction is 8. In the y direction is 0.25. And the z direction is 1.5. So my position vector ROB is 8I, remember magnitude and direction, 0.25 J plus 1.5 K feet. And therefore, my moment about point O is ROB cross F. Let's go to a fresh page and rewrite that. Let's rewrite it where F equals 400I minus 100J minus 700K pound force, and ROB we said was 8I plus 0.25J plus 1.5K. And we worked earlier, or previously in the previous lecture, using the determinant method. Remember matrices? Now for the position vector ROB, we have 8, 0.25, and 1.5. And for the force F, we have 400 minus 100 minus 700. So, taking for the first one, the I, remember we ignore the top row and the first column. So for I, that is, and we cross multiply and take the difference between like this minus this. Remember that you go this way, then minus this way. That's out between these. So that'll be 0.25 times negative 700 minus 1.5 times negative 100. This is I. Remember the J is always negative or subtraction. So now we're going to ignore the top row and the second column. That'll be 8 times negative 700 minus 1.5 times 400 J plus K, ignore the top row and the last column. That'll be 8. 8 times negative 100 minus 0.25 times 400. And this is K. Multiply these out, and you get the moment about point O caused by that force F is negative 25I plus 6200 J minus 900K pound force feet. Let's knock out another problem. This is similar to the one we just worked. You're given a force F. I minus 100J minus 700K pound force. Let me insert the picture I just drew so I don't have to work that again. Let's make that a little bit larger, like that. Okay, so here the problem's asking us to determine the moment of this force F about point A. So in this case, point A is located here. Let me do a different color. That's point A. This is my y-axis, z-axis, x-axis. I have my force F coming down at point B. Distance here is 1.5 feet. Distance here is 0.25 feet. So, and the length here is 8 feet. So in this case, we're not, in the previous problem, we worked on position vector from the origin at O because we were worried about the force, the moment the force caused about point O. So we went from O to B, but now we're going from A to B because we want to know the force is acting at B and we want to know the moment it causes about point A. So the coordinates then of A equals you have in the X direction 0, in the Y direction 0, and in the Z direction 1.5. The coordinates of B, once again, in the X direction 8, Y direction 0.25, and in the Z direction 1.5. So remember, our position vector RAB is the difference between the coordinates of point B and the coordinates of point A. This will be 8 minus 0 I plus 0.25 minus 0 J plus 1.5 minus 1.5 K. So that's 8I plus 0.25 J. And our moment about point A, let's go to a fresh page, will be R, vector RAB cross F. Once again, using our matrices determinant method, I, J, K, RAB is given as 8I, 0.25J, 0K. F was given as 400, negative 100I, negative 700, negative 100J, negative 700K. So remember for I, we ignore the top row in the first column. And this will be 0.25 times times negative 700 minus 0 times negative 100 I. And we always minus the second term for j. So this time we're ignoring the top row in the second column. So it'll be 8 times negative 700 minus 0 times 400 j. For k, we're ignoring the top row in the third column. So 8 times negative 100 minus 0.25 times 400 k. Solving this out, you get your moment about point A. It's negative 175I plus 5600J minus 900K pound force feet. Let's do another problem. Get 331 on the same page. Here, they want us to determine the moment of the force F about point P. So it's three-dimensional space, z-axis, y-axis, x-axis. It's our origin, O. We have some point here, P, and some point here, A, where the F is given as 2I plus 4J minus 6K kilonewtons. So once again, we need to know the coordinates of points P and A. Coordinates of point P, from the origin, we have to go -2 in the, or 2 in the negative x direction, or -2. So it's -2. In the y direction, it's in the negative direction as well. So that's -3. And in the z direction, that's +2. Coordinates of point A would be positive x direction 3. And this is in meters. For the y direction, that is 3 as well. And in the z direction, that's -1. So therefore, my position vector PA is just the difference in the coordinates between points A and P. So it'll be 3 minus a -2I. I'll use brackets here so it'll be a little bit clearer. 3 minus a -2I plus 3 minus a -3J plus -1 minus 2K. RPA would be 5I plus 6J minus 3K. It's meters. Therefore, my moment about point P will be RAP cross F. Using my determinants, I, J, K. RAP we said was 5I plus 6J minus 3K. The force F was given to us as 2I plus 4J minus 6K. We ignore the top row in the first column. So that would be 6 times -6 minus -3 times 4. Remember we always subtract the second term, the J term. We ignore the top row in the second column. So that's 5 times -6 minus -3 times 2j plus, now for k, we ignore the top row in the third column. So that's 5 times 4 minus 6 times 2k. Multiply all that out for your moment about point P. Get 9 is 24i plus 24j plus 8k kilonewton meters. Okay, so let's move on and talk about couple moments, a moment of a couple. This is section 3.6 in text, page 110. So a couple is defined as two parallel forces that have same magnitude but opposite directions, and they are separated by a perpendicular distance given by D. Since these forces have the same magnitude, and opposite direction, then the resultant force is 0. However, these forces do tend to produce a rotation or a tendency to rotate. So the moment of a couple is given as, in scalar, it has a magnitude of m times f, m equals f times d, where d is perpendicular distance between the two forces. In vector form, it's r cross f. With r being the position vectors, so not plural, singular, the position vector between the forces. A couple moment is a free vector meaning couple moment M can act at any point. Since the couple moment depends only on R, which is we'll say which is directed between the two forces. Resultant couple moments. Since couple moments are free vectors, their resultant can be determined by moving them to a single point and using vector addition. So the resultant, or the sum of all the couple moments, is basically M1 plus M2 plus ... Or we can write them in our vector notation. The resultant couple moment is the sum of all the individual couple moments. Take a look at a quick example on page 112 of text, example 310. It says here, determine the resultant couple moment of the three couples acting on the plate in figure 330. We draw it right quick, and a square and a triangle, basically. Three 300-pound force. F3 300-pound force. You have F1. Oh. One is 200-pound force, and the F1 force. You have an F2. This is 450-pound force. And you have an F2 force. So F3 are parallel to each other, opposite in direction, equal in magnitude. That's a couple moment they produce. The F1s are opposite in direction, equal in magnitude, parallel to each other. So they could produce a couple moment, and likewise with F2. So once again, so the resultant couple moment is the sum of all the couple moments. So it'd be, and once again, clockwise rotation is positive. Negative. Counterclockwise rotation is positive. So the F1s tend to create a negative rotation because they're making it go clockwise. So this would be the couple moment produced by the F1 forces be negative F1 times the perpendicular distance between them, D1. The F2s tend to create a counterclockwise rotation, so that would be positive times the perpendicular distance between them. And the F3s tend to create a clockwise or negative rotation. So the resultant of the individual couple moments would be the F1s. This is negative, we said. So it's negative 200 pound force. The perpendicular distance between the F1s is 4 feet. F2s we said was positive, so that's 450 pound force. The perpendicular distance between the F2 is 3 feet. And we said the F3s were negative. Perpendicular distance between the F3s is the 5 feet. Sum this up. The result of the couple moments comes up to be Let's take a look at a problem. .354 on page 117. So here, we're given a clockwise couple moment, M. M is 5 Newton meters. We have easier. This angle is 60 degrees. This angle is 60 degrees. We have reactive forces minus R. So these forces are equal in magnitude, given by the R's, opposite in direction. So they produce a couple moment. So we're given one couple moment, M, which clockwise. And it's given as 5, so it's negative 5 Newton meters. And they want the resultant of the clockwise moment M and the magnitude and the moment given by R is 2. Let me say that again. They want the resultant of the given clockwise moment of 5 Newton meters and the couple moment caused by the reactive forces R to equal 0. So they want the resultant moment to equal 0, and that has to be the sum of the given moment of 5 Newton meters clockwise and the couple moment caused by the reactive forces R. So let's take a look at that. What is the perpendicular distance between the reactive forces? D. That's what we need to get the couple moment caused by the reactive forces. Well, they gave us the B leg here, because they gave us the height here of 0.15 meters or 150 millimeters, right? And we know from our trigonometry rules, A, B, C, theta, that tan of theta is B over A. Well, they gave us B, we know theta, so we can get A, which is A, and this is A, from using tan. So then the sum of our moments, a couple moments having to equal 0. Let's bring that back down here. And we were given 5 Newton meters, negative 5 Newton meters, because it's clockwise, plus our couple moment caused by R times D. So it would be R times D, which would be 2 times, so let's work it out. I'll bring this down here so you can see it clearly. Tan of 60 degrees is B over A, which is 0.15 over A. We want A, so A is 0.15 over tan 60 meters. So 2, and it's 2 A's is the total perpendicular distance D. So it's 2 times 0.15 over tan of 60 degrees. Sum those up and set it equals 0. Solve for R. If R equals 28.9 newtons. To another problem. 357 on same page. Give a 200-pound force here. You have a 200-pound force here. They're equal in magnitude, opposite in direction, separated by a perpendicular distance of 1.5 feet. So they produce a couple moment, and you have a negative F force here and a positive F force here. 30 degrees. 30 degrees. So the F's are opposite in direction, equal in magnitude. So they produced a couple as well, a couple moment as well. They're separated by a distance of 1.25 feet. So the question says, set F to 125-pound force and determine the resultant couple moment. All right. So the resultant couple moment is the sum of all the individual couple moments. Well, we said the 200-pound force causes the moment, and it's tend to make it go counterclockwise, so it's positive. That's 200-pound force times the perpendicular distance in between them, 1.5 feet. The F's, if you take the, say, the X direction component or the horizontal component, that would be 125 times cosine of 30 degrees. Let's say negative 125, or 125 times cosine of, we'll just keep it positive. So the horizontal component is, say, 125 cosine of 30 degrees. Remember, They're equal magnitude, opposite of direction. And they're tending to cause a counterclockwise rotation as well, so it's positive. So the perpendicular distance between their components is given as 1.25 feet. So 125 times cosine of 30 to get the horizontal component, and the distance in between there is 1.25 feet. Multiplying this out, our resultant moment is approximately 435 pound-force feet. Take a look at another one. Problem 360, page 118. Determine the required magnitude of the couple moments M2 and M3 so that the resultant couple moment is 0. I'm just going to simplify this drawing right quick. So this is M2. This is at a 45-degree angle. This is M3. And you have an M1. This is 300 Newton meters. So the resultant of all these couple moments is set to, it has to be 0. Well, let's make our axes. Two-dimensional space, y is up, vertical, x-axis horizontal. So let's work M1 and M2. So my resultant couple moment in the y direction has to be 0 as well. That's a sum of all my moments in the y direction. So that would be M2 is vertical. The vertical component would be the sine of 45. So that's M2 sine of 45 degrees minus M1, which is 300, equals 0, right? Because the resultant moment has to, the total resultant couple moment has to be 0. So the individual y and x components of the resultant couple moment has to be 0 as well. Solving for M2, you get approximately 424 Newton meters. So then the resultant moment in the x direction has to be 0 as well. That's the sum of all my moments, x components. So M2 we know now is 424 Newton meters. So the horizontal x component would be cosine. So that'd be 424 times cosine of 45 degrees, positive x direction, minus M3. Therefore, M3 is 300 Newton meters. So we solved our M2 and our M3. Let's do another problem. 365, page 119. Three-dimensional space. We got Z, Y, X axis. Let's see, This is point O. You have 2 wrenches. F offset by 150 millimeters from the x-axis. This is point B, point A. This distance here is 600 millimeters. This distance here is 200 millimeters. Okay, I believe that's all we really need right now. So the question states, if the couple moment acting on the pipe, which is the moment caused by F and negative F, right, equal in magnitude, opposite in direction, the couple moment caused by force F, has a magnitude of 300 Newton meters, determine the magnitude of the forces applied to the wrenches. So M, couple moment M, is 300 Newton meters. What is the magnitude of F? So we said before that moment R, position vector R cross F. So what is we had our point A and our point B. What is my position? So let's get our coordinates of A and B. Let's get that first. Let me do that up here. Coordinates of A from the origin, you have to go 600 let's do meters. So 0.6 in the X direction, then 0.15 in the negative Y direction. And this is in meters. For B, you have to go 800 millimeters, so 0.8 meters, X direction, and 0.15 in the positive Y direction. So my position vector RAB, 0.8 minus 0.6 I plus 0.15 minus a 0.15 J. Position vector RAV is 0.2 I plus 0.3 J meters. Meters. Just rewrite that. All right, 0.2 I minus 0.3 J meters. Now my F is only in the Z direction. There's no I or J components of the F. And this is units. This is newtons. Therefore, my couple moment is RAB cross F. Using our determinant method, AB being 0.2 I 0.3J, 0K, F being 0, 0, and F for our K, right? Then solving that out, for I, we ignore the top row in the first column. So that'll be 0.3 F minus 0 times 0 I. The second term for J is always subtracted. We're ignoring the top row in the second column. So that'll be 0.2 F minus 0 times 0 J. Plus for K, we ignore the third column in the top row. 0.2 times 0 minus 0.3 times 0 K. Solve that out. You have your resultant couple moment M is 0.3 Fi minus 0.2 Fj Newton meters. Let's rewrite that. .3 Fi minus 0.2 Fj Newton meters. Therefore, they gave us the magnitude. Well, let's work it out one more time. So the magnitude of this is then square root of 0.3 F squared plus negative 0.2 F squared. So the magnitude of the moment is 0.361 F. Well, they gave us the magnitude of the moment as 300 Newton meters. So that's equal to 0.361 F. Solving for F, you get F is 832 newtons. Let's look at section 3.7. Simplification of a force coupled system. So what this section is about is reducing a system of forces and, let's say, moments to a simpler form by replacing this system with an equivalent system consisting of a single resultant force and resultant couple moment. This requires us to apply the principle of transmissibility, which states that a force is a sliding vector, meaning it can be applied at any point along its line of action. So in equation form, this comes to the resultant force of a system is equivalent to the sum of all the forces. So this is basically sum of your resultant force is just sum of all your forces, which we've been kind of working with for a while now. And in scalar form, the x component of the resultant force is the sum of all your forces in the x direction. The y component of your resultant force is the sum of all your forces in the y direction. And the resultant couple moment of the system is equal the sum of all the couple moments, which is sum of all the couple moments, plus the moments caused by all the forces about point O. And this is represented by, so the result, if I replace all the moments in the system by one resultant moment, I have to take into consideration the moment caused by all the forces in the system about the point O, plus any couple moments in the system. Took a look at an example problem. Let's look at example 314, page 123. Here they want us to replace the force and couple system shown. Let's draw it out. You have a P kilonewton force, 30-degree angle. You have a 5 kilonewton force. This is a 3, 4, 5 triangle. You have a 4 kilonewton force here. This is your point O. All right. So they want us to replace this force and couple system shown here by an equivalent resultant force and couple moment acting at point O. Okay, so we said that we can replace with a resultant force, which is the sum of all my forces, and a resultant moment system, a resultant moment about point O, which is the sum of all the moments caused by forces in the system about point O, plus the sum of all given couple moments. So starting with the forces, the sum of forces in the x direction gives me the resultant force in the x direction. So 3 kilonewton in the x direction takes the cosine of 30. Positive x direction, plus the 5 kilonewtons times the 3/5 leg ratio. This gives you 5.6 kilonewtons. Sum of forces in the y direction. That'd be the 3 kilonewton force times the sine of 30 minus 4 kilonewtons minus 5 kilonewtons times the 4/5 leg ratio. This gives you 6.5 kilonewtons. So the magnitude of the resultant force, square root of FRX squared, you get 8.58 kilonewtons. Theta, this is kind of review now from our earlier work in chapter 2. Gives you 49.3 degrees. So now for the moments, this is just now the sum of the moments caused by the forces about point O, because in this problem there was no given couple moments. So we just have to calculate the moments about point O caused by the 3 forces. All right, so for the 3 kilonewton force, the horizontal component, cosine 30 degrees, is offset from point O by a perpendicular distance of 0.1 meters. That's the perpendicular distance. The vertical component of the, and this is negative because it's causing a clockwise rotation, then the vertical component will be positive because it's causing a counterclockwise rotation. Let's bring it down here. So that'd be sine of 30 degrees. About point O, the perpendicular distance is 0.2 meters. The 4 kilonewton force causes a clockwise negative rotation about point O, and the perpendicular distance is 0.2 meters. There is no horizontal component of the 4 kilonewton force. The 5 kilonewton force, the vertical component causes a clockwise negative rotation about point B. So that's minus 5 kilonewtons. Vertical component is the 4/5 leg ratio. Perpendicular distance is 0.2 plus 0.3, which is 0.5 meters. The horizontal component causes a counterclockwise positive rotation about point O. And the perpendicular distance, once again, is 0.1 meters. Solving that out, you got the equivalent resultant moment, about point O, of negative 2.46 kilonewton meters. And since it's negative, it's saying that it's clockwise. So then we can, saying at point O, we can resolve that into a FR given by theta, which we said was 49.3s, and a clockwise here, MRO, of 2.46 kilonewton meters. And that's FR. (371) states replace the force system by an equivalent resultant force and couple moment at point O. This is two-dimensional space. We have some force here, 455 newtons. This is 12, 5, 13. And we have some force here. This is 60 degrees. This is 600 newtons. The origin, point O. So once again, sum of forces in the x direction. (600) times cosine of 60 degrees gives me the horizontal x component. The 455 is in the negative x direction, and that'll be the 12/13 leg ratio. This gives you negative 120 newtons. In the y direction. This would be the 455 newtons, which is in the positive y direction. This is times the 5/13 leg ratio minus the 600 times sine of 60 degrees. This gives you negative 344.6 newtons. My resultant force magnitude is the square root of 20 squared, 44, 6 squared, theta of 340. our resultant moments, once again, no couple moment was given in the system, so we just have to determine the moment caused by the forces about point O in this system. So for the 600 Newton force, the vertical leg will be sine. So that's 600 newtons times sine of 60. And the vertical bringing it, causing a counterclockwise, so positive rotation. And the perpendicular distance between the vertical component of the 600 Newton force and the origin is 2.5 meters. The horizontal component, which would be cosine, is also producing a counterclockwise rotation about point O. So it's positive. And the perpendicular distance there is the 0.75 meters. Now the vertical component of the 455 Newton force goes through the origin, so it causes no rotation since its line of action passes through the origin. But the horizontal component is separated by a perpendicular distance. So it's causing a counterclockwise, so positive. So we'll add the 455 times, we want the horizontal component, which would be the 12/13 leg ratio, times the perpendicular distance, which would be 2 meters. So that added up, get about 2,364 Newton meters. Let's do another problem. Problem 378, page 129. Here, right quick, we have base. We have a 300-pound force here. We have a 150-pound force here. We have a 200-pound force here. Origin here. This angle is 30 degrees. This is a 3, 4, 5 slope triangle. All right. They wanted to replace the loading here with a resultant force and couple moment at O. So our resultant force in the x direction, sum of all my forces in the x direction. So that'll be 300 times cosine of 30. Let's write that in a little neater. Plus 200-pound force minus 150-pound force times the 4/5 leg ratio. So the sum of forces in the y direction, we have the 300-pound force times the sine of 30 degrees plus the 150-pound force times the 3/5 leg ratio. 240 pounds force. The magnitude the angle theta then the equivalent resultant couple moment, about 0.0. We had no couple moments given to us in this system, so we just have to worry about the moments caused by the forces, about 0.0. So the vertical components of the 300 and 150 pound force components go through, their line of actions go through 0.0, so they do not cause a moment. So we're only worried about the horizontal components. So the 300 pound force times a cosine of 30 degrees. This is caused a clockwise, so negative, times the perpendicular distance is 2 plus 2 plus 2, which is 6 feet. The 150 causes a counterclockwise, so it's 150 pound force times the 4/5 leg ratio times 2 plus 2 feet, which is 4 feet. And the 200 pound force causes clockwise, so negative, and the perpendicular distance is 2 feet. Solve that out. Get negative 1,000. Okay, we'll call it a day at this point. If there are any questions, please do not hesitate to email me, and have a good rest of your day. Thank you.